Welcome! You ever wonder how your computer can run like a dozen different things all at once without just completely crashing? Well, today we're diving into the hidden world of how all those different programs talk to each other, and more importantly, how we stop them from fighting.
So let me ask you a question. What's the absolute worst bug to track down? It's not some simple typo, right? No, it's the one that only shows up on a Tuesday when you've just compiled and the wind is blowing from the west. It's a bug that's caused by nothing more than pure random chance.
This is the real ghost in the machine. It's the kind of bug that can bring your whole system to a screeching halt, but then, poof, when you try to make it happen again, it's just gone. It makes debugging feel impossible, because its very existence comes down to a race.
And that brings us to our main villain today, the race condition. Okay, picture this. Two different programs try to update your bank account at the exact same millisecond. One's a deposit, the other's a withdrawal. Your final balance? Well, it completely depends on which one gets to write its result last. If the timing is just a little bit off, money could literally vanish. That's a race condition.
So, to stop these kinds of chaotic races, we have to figure out where they can even happen. We got to define the battlefield. We need to pinpoint the exact lines of code where these conflicts could break out.
In this danger zone, it actually has a name, the critical section. Any little piece of your program that touches something shared, a variable, a file, a database entry, whatever, that's part of it. This is where the digital tug-of-war for control is happening.
And the #1 rule for winning on this battlefield is called mutual exclusion. The idea is so simple, but it's incredibly powerful. Only one process is allowed inside that critical section at a time. One in, one out. Period. But okay, how do you actually enforce a rule like that?
To make that rule stick, we're going to need a pretty specialized toolkit. These are the clever little mechanisms that are designed to turn that raw competition into some kind of orderly cooperation.
First up, we've got the mutex, which is short for mutual exclusion. Just think of it like a lock on a door. Before any process can step into that critical section, it has to get the lock. Now, if another process comes along and sees that the door is locked, well, it has no choice. It just has to wait outside until the first one is done and releases the lock.
You know, this restroom analogy is just perfect. A mutex is totally binary. It's either locked or it's unlocked. The key is either in your hand or it's not. There's no in-between, which is exactly what you want for that strict one-at-a-time access.
But what happens when you have more than one of something? What if it's not just a single room, but a few identical resources? That's where the semaphore comes in. Instead of a simple lock, a semaphore is a counter. When a process wants to use a resource, it just ticks the counter down. When it's done, it ticks it back up. If that counter ever hits 0, well, any new processes have to wait until someone else finishes up.
So here's the absolute key difference. A mutex is all about ownership. The same process that locks it has to be the one to unlock it, like putting the restroom key back. But a semaphore, it's all about quantity. It's like the sign at a parking garage that says 10 spots available. It doesn't care who takes a spot, just that there's a spot to be taken.
Now, these tools become absolutely critical when you're using the fastest but also the most dangerous way for processes to talk: shared memory. This is basically where the operating system lets a bunch of different programs all write on the exact same digital whiteboard. It's incredibly fast, yeah, but man, is it risky.
And here is the giant catch. That super fast whiteboard, it comes with absolutely 0 rules. By default, there is nothing stopping two processes from just scribbling all over each other's work. If you don't use tools like mutexes to act as a moderator, you are basically sending out a written invitation for a race condition to come and crash the party.
All right, so let's actually see how these tools work in a real-world kind of scenario. We're going to use a classic computer science challenge to put them to the test, the producer-consumer problem.
So in this problem, we have producers that are making items, let's just say they're making widgets, and they put them on a shared conveyor belt. Then on the other side, we have consumers who are taking those widgets off the belt to do something with them. That conveyor belt, that's our shared buffer. Okay, so this setup creates 3 really critical rules that we have to enforce. Rule 1, producers can't add a new widget if the conveyor belt is already full. Rule 2, consumers can't try to take a widget if the belt is empty. And Rule 3, this is the most important one. You can never have 2 processes trying to touch the same spot on the belt at the same time. That's our race condition right there.
And the solution here is really cool because it shows how our tools work together as a team.
We use a mutex as a simple lock, which makes sure only one worker can touch that belt at any given time. Bam! Race condition prevented. Then, we use 2 semaphores as counters. One, let's call it full slots, tells the consumers if there's anything there to take. The other one, empty slots, tells the producers if there's any space to add something. It's a perfectly coordinated dance.
So our synchronization tools, they seem like the heroes of this whole story, right? They create order out of total chaos. But what happens when our heroes are misused? What if the very tools we designed to prevent problems end up creating a new one that's even worse?
Okay, just imagine process A needs 2 things to do its job, let's say a printer and a scanner. It starts off by successfully locking the mutex for the printer. So far, so good.
Now, at almost the exact same millisecond, process B starts up. It also needs both the printer and the scanner, but it happens to grab the lock for the scanner first. So just notice the situation we're in now. Each process is holding one key and needs the other one.
And right here is where it all goes wrong. Process A, while it's still holding on to the printer lock, tries to go and get the scanner lock, but it can't. Process B already has it. So process A just grinds to a halt. It's stuck, waiting for that lock to be released.
And then comes the final fatal move. Process B, holding the scanner lock, tries to get the printer lock, but it can't get it. Process A has it. And now we have a deadly embrace. Process A is waiting for B, and Process B is waiting for A. They are stuck in a permanent standoff. They will wait forever.
This is a deadlock. It's a brand new villain, born from the very same tools we used to solve our first problem. And it's a terrifying kind of bug. It's not a loud crash, it's a silent, complete system freeze, caused by a perfect, inescapable gridlock.
You know, this whole journey from race conditions to deadlocks, it really shows a fundamental tension in computing. Gaining all that speed often means you're adding a lot of complexity, and with that complexity comes the risk of these silent, catastrophic failures. So I guess the final question isn't just about how we make our systems more powerful, but how do we build them to be powerful and predictable? How do we win the race without getting stuck in gridlock? Thanks for tuning in.